Hi, in the previous part I showed you what's possible with Ghidra and how it can be used to disassemble an STM32 bin file. We were able to find the main function and check exactly what it executes. If you missed that video, check it out, because in this one we are building right on top of it. The core concept relies on importing the SVD table into Ghidra and analyzing the address jumps to get into the code section that interests us. In today's episode, we will go a bit deeper and inject our own custom code into an already compiled file. An important note here is that the size of the file will not be affected. This makes it much harder to visually detect infected firmware. Another interesting fact is that it's possible to modify the code and yet make the original functions run without accidental crashing. You may wonder how? Let's visualize it. This is our microcontroller's memory section. It is built with the vector table, functions, constants, and global or static variable declarations. And now, with this in mind, we have a few options for injection. First, we can take an already compiled function and simply replace it, just like that. A good strategy is to replace a function that is not critical for the system. This way, it won't crash and our injected code won't be noticed until we want it to be noticed. For example, it could be a function that blinks an LED. Another way to insert code without resizing the file is to find the padding sections of free space. You see, because the memory pool space is sometimes divided into sections or pages, padding is used to ensure proper memory alignment. These padded sections shouldn't be used by any standard function calls, which makes them a perfect space for us to drop our custom functions. We just have to remember to handle the alignment and padding ourselves. Another option, and actually the one we are going to use today, is to find some large array. Preferably ones that consist of ASCII coded values, because this type of arrays are usually used to display information to the user, and since they are constants, they reside in read-only memory and not the executable memory space. We can use this space to hide our code instead of ASCII values. The absolute best case scenario is if that array is rarely read by the system. If the system does try to display this array in the user interface, it will just show up a messy memory dump. Let's go back to our C code example. Here we have our main loop with three function calls. One is blinking the diode, the second is called send_UR_data, which doesn't execute much, but it's filled with some basic assignments so the compiler doesn't optimize it away. The last one is just a delay. In normal operation, we should see the diode blinking with a frequency of 2 Hz, which is exactly what happens. I also added one extra line of code, which is a constant char array filled with some beautiful Latin text. What I'm doing here is importing the bin file to Ghidra and setting the language as well as memory mapping. Here I'm also adding the mirror, as we did in the previous examples, and loading the SVD table. To inject our code, we need two specific addresses in the memory. First, we need the address at the exact moment when we want to perform the jump to our custom function. We are going to hijack the processor precisely during the call to send our data, so we'll have to modify this assemble instruction, and the place where the instruction sits in the bin file is an offset. Next, we have to decide where we want to jump. By scrolling down, we can find our ASCII array section. This is the place where we will hide our payload. So, we take the address of this memory section and let Ghidra tell us what the instruction looks like. We just have to scroll back to the main loop, patch the instruction and write the address where we want to jump. As you can see, Ghidra tells us how the instruction should look. Now we know where to modify the bin file and what values inject to jump to ASCII array. Now for the final part, we will be replacing the ASCII array section itself, but first we need our C injection function compiled. To do that, we can just make a new project and write our code in the main function. Here, what I'm doing is making the LED blink in a loop with a frequency of 10 Hz. Next, we compile it and open in Ghidra. Here what I'm doing is the same process as before. I'm selecting the language, choosing the memory sections, and importing the SVD table. We navigate to the main function just like before. We'll need Hex Editor. I am checking where the function starts and ends. We will need offset addresses to find the function in the bin file. After opening the raw bytes in the Hex Editor, we just need to go to the beginning of the function. Ghidra tells us it's byte 332. We copy the raw bytes from that address with the length of the function, and now we have the pure binary representation of our custom function. Next thing to do is to paste those bytes over the ASCII code. In Hex Editor, I open our first modified project, the one where we copied the instruction to jump to the ASCII table, and I go to the address of the table. In this section, I paste our copied code. Now, we injected our own code to the bin file, but we still need to execute it. To do that, we have to modify one last thing in the bin file, which is an instruction jump. I open again modified bin file in Ghidra to check what is the offset of the instruction jump to send word data. Ghidra tells us it's 408. With this information, we go back to the Hex Editor and go to that address offset. Since we already know how the patched instruction with the jump to the ASCII table should look, we paste it here. One last step is testing it. Using an ST-LINK, I downloaded the modified bin file to the Bluepill board, and here we are. Our LED is now blinking at a much higher frequency every 2.5 seconds. We can do anything to hijack the entire execution flow of the device. By just changing a few specific bytes, we completely bypass the intended logic and took control of their hardware. And all without adding a single byte to the file size or triggering any obvious alarms. This is exactly why hardware security features like secure boot, memory protection units, and firmware encryption are so critical in modern embedded systems. I hope this episode gave you a solid hands-on understanding of how binary patching and reverse engineering work in the real world. If you learned something new today and want to see more, make sure to smash that like button and subscribe to the channel.